Hello everybody and welcome to the latest edition of the Physics Corner. I'm your host, Dr. Christopher Sorolla, and this is a program in which we show you how to set up and solve introductory physics problems. Today we're taking a look at static electricity. Specifically, this is an old type of problem that physics textbooks often use to illustrate how electrical forces work in interaction with electric fields and electric charges. So it's not a very practical way, it turns out, to do things, but it's a good way to illustrate how to solve the problem. So let's imagine we have the following situation. We have a small rubber stopper, which is a mass of 10 grams, hanging loosely on a string. So it pulls the string down tight, and of course is hanging due to gravity. There's tension holding the string up. Rubber holds it down, or the mass of the rubber stopper holds it down. That you're already familiar with probably by now. Now let's introduce still a little bit of a different scenario. Let's suppose we have put a little bit of electric charge on the rubber stopper. Now, that's what we're going to be searching for, so I'm not going to tell you what the number is yet. We need to find that. But we do have an electric field that's applied across the field horizontally, as shown in the picture here. And so, what this does is it makes the mass float off to the side. There's going to be an equivalent force pushing the rubber stopper to a side, and there'll be another force trying to pull it back, namely a component of the tension. So how do we go about using this knowledge to solve for the charge on the rubber stopper? So this is a callback, purposely usually, to illustrate how electricity is just another force as far as we're concerned here. So previously you've learned about forces in free body diagrams, how to set up a free body diagram, set up coordinate axes, components of forces, in order to solve problems. Well, it's the same thing, except there's one big difference, or one new addition. It's the electric field idea. So, first off, let's write this off to the side so we kind of have it in our heads. Electric forces can be described in a couple of ways. If you have an electric field in a problem, then the electric force is equal to charge, which we use the little letter Q for, multiplied by electric field. Now also, because this will become important for us, this is a vector, and we need to express it in that fashion. Now the charge itself is not a vector. The charge is a scalar. It's either positive or negative for a sign, but that doesn't indicate direction. The electric field, on the other hand, does have direction, and so the force will have direction as well. So when we're setting up a problem using forces, electric force is a vector, just like any other force is. So how do we set this up? Well, do what you've done in the past, except we're going to add in this new electric force, and here's what we mean. So let's sketch out a free body diagram. So we have a mass like that. We have tension in the string is trying to pull the mass upwards like this. We have weight of the rubber stopper itself going down, that's mg. And then there has to be one other force, because otherwise this would be accelerating, right? There has to be something to counterbalance the sideways motion that otherwise would be here, and that will be the electric force. And I'll write it as QE like that. So what we can do with this setup, when we get solving it, we'll solve for both the amount or magnitude of the charge, and we'll solve for the sign of the charge, whether it's a positive or negative charge that we've put on the rubber stopper. Okay. So that's our free body diagram. Now, there's one of these forces is off at a weird angle. That, of course, is tension. And so let's go ahead and note there's an angle. In the problem, it's a 5-degree angle, like this, that we have to account for. So if I blow up the tension vector, just the tension vector by itself for a moment, I would end up having a picture that looks something like this. Here's your angle. This then is the adjacent side to the angle. That involves the cosine, and it looks like that. This will be the opposite side, and involves the sine, as so, like this. So I could take this free body diagram and recast it to this shape. We have a t cosine theta going up and a mg going down. We'll have a QE to the left, and we'll have a t sine theta to the right. And notice that if it's floating still, this is an equilibrium problem. So what we're after eventually are the sums of forces in both directions. And because we've done this kind of obviously now, let's make it explicit. We'll put positive y going up and positive x to the right. So again, this is similar to free body diagrams for forces when you worked in mechanics. It's now that the topic's a little bit different, but if you think about it, we're just introducing a new kind of force. We're not really changing otherwise how we're doing the problem. Which means what? It means we need to find the forces in both x and y directions, or if you will, to set up force equations. All right, so force equations look like this. The net force in the x direction, or along the x-axis, will be the sum of the forces, and that is t sine theta is positive, and QE is negative, like that. Okay, so there's the sum of forces, right? And because it's standing still, then that must be no acceleration, so that equals 0. Similarly, in the y direction, this will give us t cosine theta going upwards like that, mg pulling the mass downwards, and again, same argument, net force is equal to 0. Okay. So what we're after is the charge on the rubber stopper. Now, we also could solve for the tension and get a number, but that's not the most interesting part of this problem. The interesting part is the charge. So we're going to focus on solving for the charge. And if you look at these two equations, we can do that relatively quickly. So let's recast these. T sine theta is equal to QE, and t cosine theta is equal to mg. Now, why did I write it like this? Because I'm going to take these equations and divide them. This is a trick we also used to use in solving mechanics problems of this similar types. Let's do it here. And the reason to do this particular trick is because, first of all, the t cancels. So we take two equations, reduce it to one equation, and eliminate one of the variables at the same time. And then if you notice, sine divided by cosine is actually tangent. So that gives us this as a solution. All right, in this particular problem, we're solving for Q. Okay. Another reason, by the way, to solve for Q is that would be the toughest thing to actually know or measure ahead of time. So G is a constant. Mass is something you just put the rubber stopper on a small scale. We're assuming you can measure the angle. You can use a protractor or look at the situation carefully and calculate the angle without too much difficulty. The electric field would probably be coming from some equipment which you are in control of. So all these other items are items that you have some say over, whereas the amount of charge you put on the rubber stopper is a little bit difficult to do. So let's go ahead and solve for that. So this means I have to multiply both sides by mg, divide both sides by e, and so I'll have mg over e, and then multiply by tangent theta like that. So here's the algebraic solution. Okay. Let's go ahead and plug in some numbers and see what we get for a reasonable number. So m is the mass of 10 grams or 0.010 kilograms, like that. As we often do in these series, we're going to round off g to 10 meters per second squared. Again, this is more of a demonstration type of problem than anything else. We've decided that the electric field has a strength of 1,000 newtons per coulomb, like that. And then it's tangent of 5 degrees here, all right? So if you notice, 10 times 0.01 is 0.1, divided by 1,000 is 1/10,000th, so this gets pretty small. And the tangent is a very tiny number itself of 5 degrees. You can double check my numbers when you're all said and done. I'll give you two significant digits for an answer to give you a feel for it. 8.7 times 10 to the negative 6th will be the number we get. All right, now let's take a look at the units. Kilograms times meters per second squared. That's newtons. Cancels, newtons down here. 1 over coulombs gives us back coulombs. So unit-wise, it also works out. And again, if you haven't done this for a while, this is a good strategy to always undertake whenever you're faced with a problem, especially a newer problem. Plug in the units along with the numbers so you can follow along and make sure that you get what you're supposed to get. In this case, of course, we did. All right, so there's the magnitude. Now, what about the sign? Okay, well, let's think about this a little bit. It's not going to come out of this math right here directly, so we're going to have to think about this for a moment and see what the sign's going to be. Well, let's take a look at the picture. In this case, the tension is trying to pull the mass this way. So Q times E is going to the left. But if you look at the direction in the picture, the field itself is pointing to the right. To the left is the opposite or negative, if you will, of the right. and therefore the charge must be negative. And that is a way to argue for your results. All right, everybody. Technical support is from Sidney Gautreaux and Sophia Turner. Funding for these videos comes from the University of Mississippi and University of Southern Mississippi. We record in Hattiesburg, Mississippi itself. Again, I'm your host, Dr. Christopher Sorolla, thanking everybody for your attention, and clear skies, everybody.